We have more than one independent variable, but only one dependent variable. And so this is an example. If I say f of x and y is equal to x squared plus y squared, I've got two independent variables, but there's only one dependent variable, f. Okay. We're going to do domain and range problems first. So remember, the domain of a function is the set of all allowed input values. The range of the function is the set of all possible output values. And in this class, we are only concerned with real numbers. And so if a particular number, when you plug it into the input of the function, gives you an imaginary output from your function, then that's not going to be part of our domain, okay? We only want real numbers in this class. So find the domain and range of x squared plus y squared. Well, what's my domain? Yeah. My domain would include any real number for x, right, from negative infinity to positive infinity, and any real number for y from negative infinity to positive infinity. The range of this function would be what?
Anything greater than 0.
Yeah, very good. The range would specifically be anything greater than 0, any positive real number. But I can't ever get 0 as the value of my function, and I can never have a negative value of this function. And I'm sure, you know, I haven't been around forever, but I'm sure your previous classes, showed you that double struck R notation. But I could have written it like this, I guess. An interval from negative infinity to positive infinity. What about this function? What would be the domain here? With x and y as my input variables, what is the set of all allowable inputs?
Everything but 0 for x.
You're close.
When 0, or x is 0 and y is 3. Oh, never mind. Just kidding.
So somebody tell me about the natural log function. Let's ignore the x times y part for right now, but what do you know about natural log? I can't take the natural log of...
Anything less than 0, 0 or less.
Yeah, I can't take the natural log of 0, and I can't take the natural log of any negative number, right? I can only take logarithms of positive real numbers. And so that means my domain would be the set of x and y such that x and y are greater than 0. So the little curly brackets are telling me I'm building a set. And then this reads, my set includes all coordinate pairs x and y such that x times y is greater than 0. So the vertical line, you would read that out loud by saying such that. My domain is the set of all coordinate pairs x and y such that x times y is greater than 0. The range would be what?
All.
Yeah. I think, yeah, you're right. So my range would be all real numbers. And sometimes I think it's nice. I didn't actually write this on your homework, but sometimes I think it might be a good question to ask you to draw where the domain and range are. And in this case, if I wanted to draw my domain, I would draw it here up in the first quadrant, because in the first quadrant, x times y is greater than 0. And then also in the third quadrant. The second and fourth quadrants don't get to be part of my range, or sorry, my domain, because these are the only places where x times y is positive. Yep. So if you were going to go graph this, we're probably not going to do this for every single one, but we can do this for a few of them. Let's say z is equal to natural log of x times y. Like I said, you can see that the function exists in the first and third quadrants, but it just doesn't show anything in the others. Okay. So what about this one? What's my domain? You don't think x can be 0? Why not?
You can't divide by 0.
That's true. You can't divide by 0. So that's one thing to take note of. I definitely can't have x equals 0. What else is important for my domain?
X squared plus y squared has to be greater than 9.
Yeah. If I want to avoid having complex numbers, then x squared plus y squared should be greater than 9, so I'm not trying to take the square root of a negative. So let me draw a picture of what this would look like in my domain. X cannot be 0, so my y-axis is not included in my domain. What does it look like to say that x squared plus y squared is greater than 9? And is it supposed to be strictly greater than 9?
Greater than or equal.
Yeah, I guess we could say greater than or equal to, right? Because it's okay if I take the square root of 0. 0 is still a real number, so that's perfectly fine. But what would it mean if I say x squared plus y squared has to be greater than or equal to 9? How does that look on my xy plane?
X and y intersects whenever they're at 3. It's just not shaded in. Inward out. If that makes sense. Like at x3 or y3 and x3. It'd just be the rest of it, and this box right here wouldn't be shaded.
You might be thinking about x plus 9 is greater than 9, and not x squared plus y squared.
It'd be a circle with a radius 3. Everything outside of it would be shaded in.
Yeah. X squared plus y squared equals 9 would give me a circle with radius 3 centered at the origin. So if I say x squared plus y squared has to be greater than 9, then I'm talking about that circle and all of the points outside of that circle. So here's 3, and the domain would involve all of the stuff outside of this circle. Not inside the circle, because inside the circle, x squared plus y squared is less than 9. But my domain is all of this stuff out here. And remember, not including the y-axis, right? The points that are directly on the y-axis don't get to belong to the domain either, because I'm dividing by x. But the points that do get to belong to the domain are on that circle or outside of it. And like I said, let's do some of these on the graphing calculator. Like square root of x squared plus y squared minus 9 over x. See how that looks. So right on that green y-axis, we don't get any points in the domain because my surface kind of shoots up like a, you want to call that like a vertical asymptote. And also notice that the function just doesn't exist inside the circle with radius 3. So you kind of have this slice through the function of the y-axis and then a big hole in the function too. All right, what about this one? What is my domain here?
What is the range of the last one?
Oh yeah. I already kind of spoiled it because I showed you a picture, but what is the range of this? The range is going to be all real numbers. Because I can get to any positive number I want. All I've got to do is make y greater than 3. And if y is greater than 3, then y squared is greater than 9. And so the numerator is something positive. And then I can get to any other positive number I want by just adjusting the value of x, right? I can make x like a really, really, really small number that's just barely greater than 0. And then the whole function value being divided by x could be as large as I want it to be. So I can reach all of the positive real numbers. I can do the same thing and reach all of the negative real numbers if I just make that x a negative number in the denominator. And then lastly, I can get to 0 if x squared plus y squared is equal to 9 and x is not 0. So I can get to all the real numbers if I want to. Now, the domain of this one right here.
So x squared minus y squared would have to be less than or less than 9.
Yeah, I think you're right. So I want the radicand to be positive. So that means I want 9 minus x squared minus y squared to be greater than 0. So if I add x squared and y squared to both sides, I get this, which says x squared plus y squared has to be less than 9. And honestly, it's okay to take the square root of 0. Square root of 0 is 0, but the problem this time is I can't divide by 0. So I really do need this to be strictly greater than and not greater than or equal to. So if I was going to draw my domain, and here's a circle with radius 3, what part do I shade? The inside this time, yeah. The inside of the circle with radius 3, that's where x squared plus y squared is less than 9. Ooh. Okay, Now what about the range? What's the range of this function?
Just be positive 3, negative 3.
You're saying that the range only goes from positive 3 to negative 3? Like in between those? This is a hard one. Think that. Why do you say the range should be from positive 3 to negative 3? So let me suppose for a minute that y is equal to 0. And so then I've got like x divided by square root of 9 minus x squared. Then x has to be between negative 3 and positive 3, right? Because if x were less than negative 3, then x squared would be larger than 9, and that would be a problem. If x were greater than positive 3, then x squared would be greater than 9, and that would be a problem. So if I had x equals 3, then that's 3 divided by, let's say, a really small number. Or let's say x is equal to 2.9999999. Then I've got 2.9999999 divided by, not 0, but it's a really small number. And if I divide by a really small number, then this becomes a really, really large number. And so it seems like that way I could actually reach all of the positive real numbers just by choosing a value of x that's like arbitrarily close to 3. If I wanted all of the negative real numbers, I could just choose a value of x that's like arbitrarily close to negative 3. And again, this would be a really small positive number in the denominator, but I would have a negative numerator, and so that would give me the negatives. I can get 0 just by setting x equal to 0. So I think the range is, I think it might be all real numbers again. It's always good to check and see what our surface shows, but I think the range could get us to all real numbers. We're doing x divided by square root of 9 minus stuff. X divided by square root of 9 minus x squared minus y squared. Okay, so sure enough, the domain is just inside that little circle with radius 3. The function doesn't exist outside of that. And it does seem like I can get to all of the real numbers, because it shoots up to the positive infinity on one side and down to the negative infinity on the other side. And it passes through 0 at the y-axis, so perfect. What about this one? What's my domain? Oh, this is an interesting function because this time I have 3 independent variables and 1 dependent variable. Yeah. Yeah, there's no restriction on my domain. X, Y, and Z are all allowed to be any real number they want to. So, this double struct capital R with a superscript 3 is shorthand math notation for saying three-dimensional real number space. So you could write that if you want to say X, Y, and Z can be all real numbers. No restriction on the domain. What about my range? And by the way, I don't know if the symbols I'm using make any sense. If you ever have a question about what I'm writing, just raise your hand and ask me. But if you see this weird little symbol, when you read it out loud, say the words belongs to. So like the coordinate triple X, Y, and Z belongs to the three-dimensional real number space. Or F belongs to, and then we're about to write some kind of interval for F. So what's the range of this function? Yep, I can get to all the real numbers just by setting Y and Z equal to 0, and then X can be whatever it wants, and that means I can reach all the real numbers with this function. Okay, what about this one? What's my domain for the natural log of X times Y times Z?
It can't be 0.
It's true. So I'm talking about the set of all coordinate triplets such that
X times Y times Z has to be greater than 0.
Yep. The deal with natural log is that the argument has to be a positive real number. So X times Y times Z has to be greater than 0. What is the range of this function?
All real numbers.
It's, again, all real numbers. Because after I take care of the domain, this is just the natural log function, right? So the range of the natural log function is all real numbers. Okay. I don't know how many more we have left, but I think we have a plentiful amount of time to talk about all these. So yeah, we got one more. One more. What's the domain of this function?
X can't be 0.
Very good. We can't divide by 0, so x cannot be 0. What else?
X squared plus Y squared plus Z squared has to be greater than 25.
Mm-hmm. Yeah, greater than or equal to 25. So what would that look like? I'm not going to try to draw it because I'm not a good three-dimensional person. But what would it look like to have x squared plus y squared plus z squared be greater than or equal to 25?
A sphere with the intersects at 5.
Yep. We are talking about the points in space that are on or outside of the sphere with radius 5 centered at the origin. And x can't be 0. So no points in the yz plane get to be in our domain either. And then once again, I think that our range is all real numbers. So there's not a lot of variety in the range. There's a few that weren't all real numbers for the range, but I think that's the case. So you know, with these functions of two variables, we can plot them on GeoGebra and see functions of two variables as surfaces in space, where the z is the output variable and the x and the y are the input variables. Whenever you have a function of 3 input variables, you can't really graph that. You know, you can't graph 3 independent variables and 1 dependent variable together. The way you can think about it is by thinking about a scalar field. And a scalar field is this idea of like, okay, 3-dimensional space, it's like where we live, but every point in space gets assigned a number. An example of a scalar field might be temperature, right? Every single point in space has a temperature. Just go put a thermometer on it and you can measure the temperature. So that's a way to assign a single scalar numeric value to every point in space. Think about temperature, or barometric pressure, or I don't know. In the manufacture of solar panels, you start off with a big block of just silicone, like as pretty pure silicone. And then you do a process called doping. And when you dope the silicone wafer to make a solar panel, you press one side of it against, I want to say boron, and the other side of it you press against phosphorus. And so you've got like 3 solid layers. You've got the boron layer, the silicone layer, the phosphorus layer. And you press them really tight together, apply some pressure. You heat it up quite a bit. You don't want to melt anything, but you want it to be hot enough so that the atoms feel like they can move and diffuse from one solid to the next a little bit. And that's exactly what happens. Some of the boron migrates into the silicone. Some of the phosphorus migrates into the other side of the silicone. And then you've got this silicone wafer that has a gradient of concentrations of boron and phosphorus throughout. And so another kind of idea of a scalar field might be like, okay, in that 3D solid, every point inside the 3D solid has a certain concentration of boron. That could be your scalar field. Sorry, I'm really grasping for straws at examples here, but scalar fields have usefulness. Okay, this is a calculus 1 thing, so maybe you guys can answer these questions really quickly. Find the limit of each of the following functions as x approaches 0. So if I asked you for the limit as x approaches 0 of x cubed minus x, what is that? It's just 0. Because it's 0 cubed minus 0, right? So you can just directly plug that in. What about this one? What about this g function? What is that limit?
X approaches 0.
Yeah.
Oh, no, I'm just kidding. Infinity. I'm just kidding. One.
It's not defined. You're right the first time. Because if x was going to approach 0 from the right side, that limit would be 1. And if x was going to approach 0 from the left side, that limit would be -1. So if the right side limit and the left side limit, they don't meet up at the same value, then the limit doesn't exist. And this graph, right, is, it looks like this, right? It's positive 1 on the right side, it's negative 1 on the left side, so the right side limit is positive 1, the left side limit is negative 1, and they don't meet up, so the limit doesn't exist. What about this one, 1 over x? What's the limit as x approaches 0? Undefined. Because that graph looks like this, kind of. That's the point where x is equal to 0. Again, one side is shooting up to positive infinity, the other side is shooting down to negative infinity, and so it does not exist. You could say undefined, or you could say D and E for does not exist. Either way. Now what about this one? What about 1 over x squared? What's the limit as x approaches 0? It does exist. Because x squared is always positive, right? Even if x is a negative number, x squared is a positive number. So what does this graph look like? It would be positive on the left, and it would be positive on the right. And so this limit, as x approaches 0, of g is positive infinity. So it does exist, but the limit is positive infinity. What about this one? I'm sure everybody knows this one. What is my favorite limit? Yeah, you can use L'Hopital's rule. And L'Hopital's rule, if you apply L'Hopital's rule, says since I've got a 0 divided by 0, I've got an indeterminate form. I can take the derivative of the numerator and the derivative of the denominator, and I can evaluate the limit that way. But I mentioned limits just to keep this fresh in your mind, because now we're going to do some big boy limits. That's the technical term. We are going to find the limit of this function, x squared minus y squared, as we approach the point 0, 0 in the xy plane. And in this case, it's very, very easy. In this case, all we need to do is say that I'm going to plug in x equals 0 and y is equal to 0. And the limit is 0. That was always the easiest kind of limit, right? Is where your function is actually continuous at that point. And if your function is continuous at that point, then you just plug the things in. You just plug in x equals 0, y equals 0. Everybody always hopes for that kind of question on their Calculus 1 test. Now, new function, 1 over x times y. What is the limit as x and y approach the point 0, 0 in the xy plane? Let's think about it, or let's at least talk about it. Maybe you already know the answer, but we need to discuss this a little bit. So here's my xy plane. When I talk about approaching this point 0, 0, there's more than one way I can approach this. For one thing, I could approach it from this direction. this direction is along the line where y is equal to x. So let's pretend for a moment that we're going to approach this point with a sequence of points and try to evaluate the limit along this line where y is equal to x. To do that means I'm taking the limit as x and y approach 0, 0 of 1 over x squared. And I can say x squared because specifically I've chosen the direction where y is equal to x. So all I've done is I've replaced the y with x because that's the direction I chose to go along, where x and y are the same. And so from this direction, I know that limit as x approaches 0 is plus infinity. Let me try a new direction. On this blue line, y is equal to negative x. And so if I were to take the limit as I approach 0, 0 from that direction, this would be taking the limit as x approaches 0 of negative 1 over x squared. And again, the reason is because if I choose to approach this point from the blue direction, y is equal to negative x, so I could exchange this y with a negative x, and I've got 1 divided by x times negative x. That's negative x squared. And this limit is negative infinity. And so because these don't agree, so the limit does not exist. Just like back in calculus 1, if your right-sided limit and your left-sided limit didn't agree with each other, then the limit doesn't exist. Same thing in calculus 3. Choose any two directions, and if the limit doesn't agree, approaching from any two directions, then the limit doesn't exist. In calculus 3, all directions that you can possibly approach this limit point have to agree on what the limit is. So aside from rectangular coordinates, we can also represent points and curves in 2D space using polar coordinates. I think this probably looks familiar to you guys. Do you remember what polar coordinates are? And how we convert between rectangular and polar? So if I want to convert from rectangular to polar, and my polar coordinates give me some lowercase r and some theta. That's the distance from the origin and the angle from the positive x-axis measured counterclockwise. Then r is equal to what? Very good. X squared plus y squared. And then theta is equal to, arctangent of y over x. And plus maybe pi, right? Don't forget about that part. If you are in the second or third quadrant, you got to add pi to get the right theta. And if you want to convert from polar to rectangular, how do I find x? X is equal to what? R cosine theta. Y is equal to r sine theta. Okay, glad we remember this. You remember looking at this picture of how we can map the same 2D space in polar by choosing a point in space and saying, okay, this is 8 units away from the origin, and the angle that this point makes with the positive x-axis is pi over 3. So it's a different way to give a location in 2D space. maybe we skip over these, because I think we did this earlier in the semester. Maybe we didn't do this with polar and rectangular, but we did it with cylindrical and rectangular earlier. So think about this. Now I want to find the limit as I approach 0, 0 in the xy plane. Of this function. Well, let's draw a picture and I'll walk us through a few of these things like we did earlier. For one thing, I could choose to go along the direction where y is equal to x. And then I would get the idea that I'm taking the limit as x approaches 0 of 1 minus cosine of 2x squared, right? Because it would be x squared plus x squared if I do y equals x, divided by 2x squared. In this limit, I'll end up having cosine of 0 divided by 0. Cosine of 0 is 1. And from this direction that I've shown in blue, all the x values are positive. So I'm talking about approaching positive 1 in the numerator and approaching 0 in the denominator, where both the numerator and denominator remain positive. So this part, the term with cosine divided by 2x squared, is going to approach positive infinity, right? Can we agree? And so if I've got 1 minus a term that's approaching positive infinity, then this limit would be negative infinity because of this minus sign. Let's choose another direction and think about this one. What if I approach from this side using the line y equals 0? So my limit as x approaches 0 would be 1 minus cosine of x squared divided by x squared. And even though along that orange line, even though along that orange path all of my x values are negative, it actually doesn't really matter because I'm squaring it, right? Every time x appears in this formula, it says x squared. So a negative number squared is still positive. And so I still have cosine approaching positive 1, and I still have x squared approaching 0. And even though x is approaching 0 from the left side, x squared is approaching 0 from the right side. And so we're still talking about 1 minus a term that's approaching positive infinity, and so the limit is still negative infinity. And I'll go ahead and spoil it for you. We could do this a bunch of different ways, right? Like I could draw a line here, and we can approach from the line where x is equal to 0. And we could draw a line here, and we can approach along the line where y is equal to negative x. And in fact, you could even choose this line where y is equal to negative 1/2 x, right? There's infinitely many choices that you could choose to approach this point in the xy plane. Infinitely many different paths that you could try to approach this point with. So the problem is this: if I were to ever find a limit besides negative infinity, when I do this approach of just taking different paths and finding a limit, If I ever found anything that was anything besides negative infinity, then the limit doesn't exist. How do I know if this limit exists or not? Right? Can I ever stop taking limits? No. I would never, ever, ever be assured, even if I took 999 different limits from different directions. I could never go to bed at night. I would always lie awake wondering if maybe the 1000th direction I chose was going to be something else, and the limit really didn't exist, you know? Everybody struggles with that. So here is the trick of the day that solves our insomnia problems. Rather than choosing different directions, we are going to make a polar coordinate switch, which means I remember from polar coordinates that r squared is equal to x squared plus y squared, isn't it? So if I wanted to, I could rewrite this as the limit as r approaches 0 of 1 minus cosine of r squared divided by r squared. Again, this is still 1 minus this term that's approaching positive infinity, so the limit's still negative infinity. But the great part now that in polar coordinates, we never defined what theta. Does that make sense? This formula makes no mention of theta. And if theta is kind of the direction from which I'm approaching the origin, that means that every choice of theta will give me the same limit. And so now we're happy.
Can you say that one more time? Just the exact same way, just say it again.
Well, now I don't remember what I said. Now I can't repeat it. But that's true. You can go back and listen to the recording. But whenever I say r approaches 0, and I don't tell you what theta we're choosing, that could be approaching 0 from any direction. Theta is the direction in polar coordinates. And what I just showed is you don't even have to choose a direction, and you get the same limit. So now we actually know that this limit does exist. We don't have to wonder about what if we just chose a different direction. Okay? Let's try the same trick. Let's say we want to take this limit and we're going to switch to polar from the get-go so we don't waste our time. And polar means that r squared is equal to x squared plus y squared. X is equal to r cosine theta, and y is going to be equal to r sine of theta. So whenever I take this limit, I'm taking the limit as r approaches 0, because I'm approaching the origin again. All of these problems we're going to do with the limit at the origin, approaching the origin. And you could take the limits as you approach different points just by doing a little translation. Let me see if this makes sense to you. Well, I'll come back to that thought. We'll stick with the problem right now, and then after we solve this, I'll go on a rant. X times y is then r squared times cosine theta times sine theta. X squared plus y squared is r squared. The r squareds cancel. And so the limit, as r approaches 0, of cosine theta times sine theta is what?
that because there's no R? What?
It doesn't exist because it depends on the direction. If I'm telling you that the limit depends on what direction you take as you approach the limit, then the limit doesn't exist, right? You can't have one limit as you approach from this direction and a different limit as you approach the same point from a different direction. That's when we say the limit doesn't exist. And what this is telling me is that depending on my choice of theta, well, this limit could be a whole bunch of different things.
Does anytime theta appear doesn't exist?
Right.
Okay.
If you can't get the thetas to cancel out in the end, then it's no good. In fact, this is a great time to use GeoGebra. xy over x squared plus y squared. And we'll see what that looks like. So we're taking the limit as we approach the origin. But the problem is some directions where I approach the origin, I'll get the number positive 1/2. Other directions when I approach the origin, it looks like I get the number negative 1/2. Some directions, like if I approach along the y-axis or along the x-axis, I get a limit of 0. Do you see why that little pinch in the fabric is an issue? That's why the limit doesn't exist. Let's also take a look at the image we get if I were to graph 1 minus cosine of x squared plus y squared and see what that looks like. Because we said that this limit was going to be negative infinity. So this is 1 minus cosine x squared plus y squared divided by x squared plus y squared. And sure enough, it doesn't matter what direction I approach from, there's just a big pit there at the origin. So the limit's negative infinity. Y'all try this one. We've done a few in class together. See if you can do this one. I'll keep thinking and you work this problem. Do you guys get the same thing as me? What's my limit?
Is it just 1?
It is 1. So we still have some thetas hanging out, but they're all multiplied times r squared. And in the limit, as r approaches 0, this limit is 1. So all the other stuff goes to 0. The cosines and the sines and the cosine squared and the sine squared, those are bounded between -1 and +1. You don't have to worry about those like growing faster than the r squared function is shrinking or anything like that. So this term is going to shrink to 0 in the limit for every direction theta. And that means the limit should be 1. So let's try to graph it. 1 plus. I can't get the number in between the parentheses, it won't let me. So that's why GeoGebra sucks.
Plus xy.
Oh, it was plus xy?
Yeah.
Thank you. Okay. So that's what my function looks like. Nice purple surface. Very pretty. And you can tell no matter what direction I choose, the limit as you approach the origin there is 1. And then we've got to the end of my notes here. The last thing you should be aware of is just this definition. If you've got a multivariable function, that function is continuous if and only if the limit exists at that point, meaning the limit taken from every direction of approach is the same and it exists. And when I evaluate the function at that point, we get the same thing, right? That's another important part of this, is that the limit and the value of the function itself have to be the same for a function to be continuous. And then we say a multivariable function is continuous over a particular set if and only if it's continuous at every point in that set. Same definitions you saw back in Calculus 1, but now when we talk about a multivariable function, sometimes your set is not just like an interval along the real line. We don't just say, oh, this function is continuous from like -3 up to 5. But now with multivariable functions, your set could be some kind of region in the xy plane or some kind of region in space.